October 14, 1942. Dawn breaks over Henderson Field, Guadalcanal. The airstrip lies shattered beneath a coral dust sunrise. 53 massive craters pock the runway like lunar wounds, each one 15 feet across and 8 feet deep. Fuel dumps still smolder from the night's devastation. Aircraft revetments lie twisted into unrecognizable metal sculptures. The control tower has simply vanished. 11 hours earlier, Japanese battleships Kongo and Haruna had unleashed 900 shells from their 14-inch guns in the most devastating naval bombardment of the Pacific War. Each shell carried 1,400 pounds of high explosive, designed to render Henderson Field inoperable for weeks. Japanese radio broadcasts from Rabaul triumphantly announced the airfield's destruction. At 7:30 a.m., Chief Machinist's mate William Peterson of the 6th Naval Construction Battalion wipes coral dust from his goggles and climbs aboard his Caterpillar D4 bulldozer. Around him, 300 Seabees work with mechanical precision that transforms catastrophic damage into operational capability. The first F4F Wildcat roars down the patched runway and climbs toward the morning sky. Total repair time, 7 hours and 30 minutes. This resurrection violated every principle of military engineering that Axis forces understood, and it was only the beginning of American construction miracles that would redefine the very nature of warfare itself. When German High Command received intelligence reports about American construction capabilities in late 1942, they dismissed them as propaganda. The Wehrmacht's own engineering experience suggested that major infrastructure projects required months of careful planning and execution. Their conquest of Europe had been built upon this understanding. The Atlantic Wall represented the pinnacle of German engineering doctrine: massive concrete, to fortifications, precisely engineered obstacles, and carefully calculated defensive positions that exploited natural terrain features. Construction had taken 3 years and consumed millions of tons of concrete. German engineers measured success in permanence and precision. American forces operated on fundamentally different principles that German intelligence failed to comprehend. Where Wehrmacht doctrine emphasized careful preparation and methodical execution, American military construction prioritized speed and adaptability. This philosophical divide would prove catastrophic for Axis planning across all theaters. The European theater initially reinforced German assumptions about construction timelines. The D-Day landings required months of preparation, with Mulberry harbors representing precisely the kind of careful prefabrication that German engineers understood. But these visible preparations masked the real revolution happening in American military construction. The Pacific War revealed capabilities that violated every assumption about military engineering. Islands transformed into operational bases in days rather than months. Airfields appeared where virgin jungle had existed the week before. Bridges spanned rivers that enemy forces considered impassable barriers. The scale and speed defied traditional military calculations. German observers in the Pacific, particularly naval attachés and intelligence officers, filed reports that Berlin dismissed as exaggeration. The idea that American forces could build operational airfields in 20 days through triple canopy jungle seemed impossible. Wehrmacht engineers required 3 months to build comparable facilities in occupied Europe, with access to existing infrastructure and unlimited labor. The intelligence failure stemmed from fundamental misunderstanding of American industrial integration with military operations. German military construction relied on traditional engineering methods adapted for warfare. American military construction represented civilian industry directly projected into combat zones, bringing capabilities that had never been tested under fire. This integration created force multiplication effects that German planners never anticipated. A single American engineering battalion deployed with more mechanized equipment than entire German construction regiments. Bulldozers, power shovels, concrete mixers, and specialized machinery arrived as standard equipment rather than precious resources to be carefully allocated. The psychological impact on German forces proved as significant as the tactical advantages. Wehrmacht defensive doctrine assumed that natural obstacles would provide predictable delays based on German engineering capabilities. When American forces consistently overcame these obstacles in impossible timeframes, the entire defensive strategy became obsolete. The revolution began in March 1942 with the formation of naval construction battalions. The concept violated traditional military organization by recruiting directly from civilian construction industry, bringing expertise that regular military engineers couldn't provide. These weren't soldiers trained in construction. They were construction workers trained as soldiers. Admiral Ben Moriel, chief of the Bureau of Yards and Docks, understood what German intelligence missed. Modern warfare required construction capabilities that exceeded traditional military engineering. The solution wasn't better military construction, but military organization of civilian construction expertise. Each construction battalion consisted of approximately 1,000 men organized into specialized companies that mirrored civilian construction firms. Earth-moving specialists, concrete workers, equipment operators, and maintenance crews brought industrial methods directly to combat zones. More importantly, they deployed with equipment that multiplied human capability exponentially. A standard Seabee battalion included 18 bulldozers, 8 power shovels, 16 dump trucks, concrete mixers, pile drivers, and specialized tools that Axis engineers had never seen in military operations. This equipment represented industrial capability projected across thousands of miles of ocean, creating construction capacity in remote locations that exceeded many civilian projects. The organizational innovation proved as important as the equipment. Seabees operated under military discipline but retained civilian construction methods and standards. They built infrastructure for permanence rather than temporary military expedients, creating bases that could support sustained operations for years rather than months. The scale of deployment dwarfed anything attempted in military history. By 1944, peak naval construction battalion strength reached 325,000 personnel, with approximately 80% serving in Pacific operations. These forces represented the largest construction organization ever assembled, civilian or military. Training programs compressed years of construction experience into months of intensive instruction. Civilian construction workers learned military organization and combat skills. Military personnel learned industrial construction methods and equipment operation. The result was hybrid capability that combined military discipline with civilian expertise. Supply systems evolved to support this unprecedented construction effort. Bailey Bridge components, pierced steel planking, concrete materials, and specialized equipment moved through logistics pipelines that maintained forward stockpiles despite intensive consumption. American industry adapted to produce construction materials at wartime scales. The strategic implications became clear as operations expanded across the Pacific. Each captured island became a construction project that transformed enemy territory into Allied operational base. The timeline of conquest compressed from years to months as engineering capability eliminated geographic barriers that traditional military doctrine considered decisive. German observers struggled to understand this transformation of warfare itself, where construction speed became as important as tactical skill in determining strategic outcome. The technological superiority that stunned Axis forces began with machines that represented different eras of warfare compressed into the same conflict. A single Caterpillar D7 bulldozer generated 80 horsepower through steel tracks that could grip any surface, moving 200 cubic yards of material per hour. This exceeded the daily output of 100 German or Japanese laborers using traditional hand tools. American forces deployed these machines in quantities that defied enemy comprehension. The Seabees operated over 4,000 bulldozers across the Pacific theater, creating earth-moving capacity equivalent to hundreds of thousands of manual laborers. When German intelligence reports described this mechanization, Wehrmacht planners assumed the numbers were propaganda exaggerations. The Clark airborne bulldozer represented innovation specifically designed for rapid deployment. Weighing only 9,000 pounds, it could be delivered by C-47 transport aircraft directly to captured airfields. These machines began runway construction before enemy forces could organize effective resistance, creating the infrastructure necessary for follow-up operations. Beyond individual machines, American engineering operated as integrated systems that combined multiple capabilities. Bulldozers for clearing, scrapers for grading, rollers for compaction, trucks for transport, generators for power, and specialized tools for every construction task. German engineering units operated with equipment that had changed little since the First World War. The Seabees revolution extended beyond equipment to organizational methods that transformed military construction. Recruited from civilian industry, they brought techniques and expertise that regular military engineers couldn't provide. Master Chief Construction Mechanic Frank Morrison, with 20 years in commercial construction, explained the difference. Military engineers think in terms of good enough. Civilian contractors think in terms of fast enough. This speed differential shocked enemy forces who calculated construction timelines based on their own capabilities. Japanese military doctrine calculated that major runway damage should render an airfield inoperative for 2 to 3 weeks minimum. Complete runway reconstruction demanded 2 to 3 months using available local materials and standard engineering methods. American Seabees violated these calculations through mechanized methods and prefabricated materials. Where enemy doctrine assumed sequential repair procedures, American forces worked simultaneously across multiple damage points. Crater repair, debris clearing, and surface restoration proceeded in parallel rather than sequential operations. Traditional military construction emphasized permanence and defensive strength. American military construction prioritized operational capability and construction speed. This fundamental difference in philosophy created capabilities that enemy forces couldn't anticipate or counter effectively. The integration of civilian construction expertise with military organization gave American forces advantages that traditional military engineering couldn't provide. Commercial construction methods, industrial equipment, and private sector innovation combined with military discipline and strategic planning to create unprecedented capability. The intelligence failures that crippled Axis defensive planning stemmed from Seabees' thematic underestimation of American industrial integration with military operations. German and Japanese intelligence agencies focused on traditional military capabilities while missing the revolutionary fusion of civilian expertise with combat operations. Wehrmacht intelligence officers analyzed American order of battle, equipment inventories, and tactical formations with characteristic thoroughness. But they failed to comprehend the industrial support networks that delivered construction capability directly to combat zones. This blind spot proved catastrophic for defensive planning across all theaters. Japanese military intelligence suffered from similar limitations, focusing primarily on tactical dispositions with minimal attention to technical capabilities and industrial support systems. The Japanese Army's intelligence apparatus had never encountered military construction that operated at civilian industry scales and speeds. Captured Japanese documents revealed growing recognition that American engineering capabilities had made traditional defensive strategy obsolete. A staff study from Imperial General Headquarters acknowledged the fundamental problem. American construction speed eliminates natural barriers as defensive assets. Rivers no longer provide predictable delays. Mountain terrain offers temporary obstacles only. The psychological warfare aspect of American construction speed proved as devastating as the tactical advantages. Enemy forces experienced demoralization when positions calculated to hold for weeks fell within days due to infrastructure that appeared overnight. The very landscape seemed to transform at impossible speed. A diary recovered from a Japanese officer during the New Guinea campaign provided insight into enemy perceptions. The Americans advance with their machines like a river that cannot be stopped. Yesterday there was jungle. Today there is a road. Yesterday there was a river. Today there is a bridge. This psychological impact extended beyond individual reactions to strategic demoralization. Japanese defensive doctrine had been based on assumptions about American capabilities that proved catastrophically wrong. Islands that should have been impregnable due to natural barriers fell to forces that built their way across any obstacle. The industrial integration that amazed enemy observers represented direct technology transfer from American civilian industry to military operations. Caterpillar bulldozers, international harvester trucks, and specialized construction machinery had been developed for commercial projects, then adapted for military use without fundamental design changes. This civilian-military integration operated in reverse as well. Military requirements drove innovations that improved civilian construction methods. Bailey Bridge principles influenced post-war commercial bridging, heavy equipment modifications for Pacific conditions, advanced bulldozer and excavator design. The scale of American construction in the Pacific Theater overwhelmed enemy comprehension and planning capabilities. According to Bureau of Yards and Docks records, naval construction battalions built 111 major airstrips, 441 piers and war ves, and over 5,000 miles of roads, much through terrain that enemy forces considered impassable. The resurrection of Henderson Field on October 14, 1942, represented the moment when American construction capabilities shattered enemy assumptions about military engineering. What Japanese commanders calculated would require weeks of reconstruction was completed in hours, creating a template for construction miracles that would define Pacific warfare. The bombardment had been precisely calculated to inflict maximum damage. 914-inch shells, each weighing 1,400 pounds, created 53 major craters and countless smaller damage points across the entire airfield complex. Japanese naval commanders had studied Henderson Field's construction and calculated the destruction would render it inoperable for minimum 3 weeks. Chief Machinist's mate William Peterson and the 6th Naval Construction Battalion approached the devastation with systematic precision that transformed crisis response into assembly line efficiency. Working in 12-hour shifts around the clock, they demonstrated capabilities that redefined what was possible in combat zones. The mechanics of rapid airfield repair followed procedures that violated enemy understanding of construction timelines. Damage assessment teams confirmed crater locations and dimensions while specialized repair crews deployed with predetermined equipment loads and material requirements. The entire operation proceeded with industrial efficiency rather than military improvisation. Crater repair began with explosive ordnance disposal, as unexploded shells had to be removed or detonated in place. Bulldozers then pushed debris and soft earth from crater edges, creating uniform slopes for fill material. D4 caterpillars could clear a 15-foot crater in 45 minutes, working in pairs to maximize efficiency. Fill material came from pre-positioned stockpiles of coral and broken rock transported by 6-yard dump trucks operating in continuous cycles. A standard 15-foot crater required approximately 40 cubic yards of fill, compacted in 12-inch lifts using pneumatic tampers. Under optimal conditions, crater filling took 3 to 4 hours per location. Surface restoration used pierced steel planking, standardized sections measuring 10 feet by 15 inches and weighing 66 pounds each. PSP could be laid directly over compacted fill, creating operational runway surface within hours rather than days. A 6-man crew could lay 1,000 square feet of PSP in 2 hours. The October 14th repair operation involved simultaneous work across the entire runway system. 12 bulldozers, 18 dump trucks, and 200 personnel worked with coordination that amazed Japanese observers monitoring from surrounding hills. Crater filling proceeded from both ends toward the center, allowing partial operations even before complete restoration. By 0600 hours, a 3,000-foot section of runway was operational for fighter aircraft. By 0730 hours, the full 4,900-foot strip was available for all aircraft types. The timeline shocked Japanese planners who had calculated similar damage would require weeks to repair using their own methods and equipment. The psychological impact on enemy forces was immediate and devastating. Japanese radio intercepts revealed confusion and disbelief at American construction capabilities that violated every principle of military engineering they understood. The Bailey Bridge system, adopted by American forces, created river crossing capabilities that eliminated water obstacles as strategic barriers, fundamentally altering the nature of defensive warfare. What enemy commanders calculated as impassable barriers became mine, or delays measured in hours rather than weeks. Each Bailey panel measured exactly 10 feet long by 5 feet high, weighing approximately 570 pounds. Standardized connections allowed infinite configuration possibilities. Single-story bridges for 30-ton loads, double-story for 60-ton loads, triple-story for maximum capacity. Spans could reach 200 feet without intermediate supports using standard configurations. The launching method that amazed enemy observers involved assembling the complete bridge on one bank, then pushing it across the gap like extending a massive drawer. No heavy cranes were required, just coordinated effort from trained crews using rollers and guide systems. This technique enabled bridge construction under fire while maintaining tactical surprise. Lieutenant Colonel Samuel Sturgis Jr., commanding the 36th Engineer Combat Regiment in New Guinea, documented enemy reaction to Bailey Bridge construction in his official report. Enemy observation posts would monitor bridge sites for days, unable to understand how complete bridges appeared overnight where impassable rivers had existed the day before. The Wau Salamaua operation in New Guinea provided the clearest demonstration of Bailey Bridge capabilities, defeating enemy defensive calculations. The 114th Engineer Combat Battalion built a 120-foot double-story Bailey Bridge across the Kamatam River in 14 hours, enabling advance of 32nd Infantry Division armor that Japanese forces never expected to encounter in mountain terrain. Working under sniper fire and daily air attacks, 40 engineers assembled 24 Bailey panels with connecting hardware and deck sections. The bridge carried its first Sherman tank at 0800 hours on the second day, 14 hours after assembly began. Japanese defensive positions on the far bank had been calculated to hold for weeks against infantry attacks. These positions collapsed within hours when faced with tank support that shouldn't have been possible according to Japanese engineering calculations. The psychological impact extended beyond tactical surprise to strategic demoralization, as defensive doctrine based on natural barriers became obsolete. The Markham River crossing demonstrated how American bridging capabilities trapped enemy forces in operational tempo they couldn't match. Multiple river systems had been incorporated into Japanese defensive planning as natural barriers requiring weeks to overcome. The 2nd Engineer Special Brigade approached these obstacles with equipment that enemy scouts couldn't identify. Company A of the 533rd Engineer Boat and Shore Regiment built an assault bridge across the Markham River while Japanese machine guns fired from the opposite bank. Working in 2-hour shifts to minimize exposure, they completed a 180-foot single-story Bailey Bridge in 18 hours of cumulative construction time. Japanese defensive doctrine had calculated the Markham crossing would require minimum 3 weeks using conventional methods. Seeing American armor on their side of the river within 24 hours shattered confidence in natural barriers as defensive assets. Staff Sergeant Robert Martinez described enemy reaction. You could see them with binoculars just standing there staring at our equipment, trying to figure out how we could build bridges so fast. The strategic implications became clear as American forces repeatedly overcame obstacles that enemy planning assumed would provide predictable delays. Rivers, gorges, and mountain passes that should have channeled American advances into prepared killing zones instead became minor inconveniences overcome through construction speed that defied military calculations. The strategic implications of American construction superiority extended far beyond individual tactical victories, fundamentally altering the nature of warfare across all theaters. Enemy forces discovered that geographic advantages they had relied upon for defensive planning no longer provided predictable delays or channeled enemy movements into prepared positions. The island-hopping campaign succeeded because American engineers could transform captured islands into operational bases faster than enemy forces could mount effective counterattacks. Each island became a stepping stone for the next advance, compressing the timeline of Pacific advance beyond Japanese strategic calculations. Tarawa demonstrated this principle in its most dramatic form. Marine assault forces secured the island on November 23, 1943, after 3 days of intense fighting. The airfield was operational within 72 hours, supporting operations against the next objectives before Japanese forces could reinforce or counterattack. The 18th Naval Construction Battalion accomplished this transformation using methods that violated Japanese understanding of airfield construction. Working around the clock with portable equipment, they cleared battle damage, filled shell craters, and laid pierced steel planking, while Marine engineers provided security against remaining enemy positions. Admiral Raymond Spruance, commanding 5th Fleet, noted the strategic impact in his action report. Rapid base development enables continuous offensive operations without pause for extended construction periods. This operational tempo prevents enemy forces from organizing effective resistance or counterattack. The Tinian construction project represented the ultimate demonstration of American engineering scale and speed. Between July 1944 and May 1945, the 6th Naval Construction Brigade transformed a captured Japanese island into the world's largest bomber base. North Field contained 4 parallel runways, each 8,500 feet long and capable of launching B-29 super fortresses for 3,000-mile missions to Japan. Japanese forces had spent months fortifying Tinian using traditional methods: manual coral quarrying, hand-mixed concrete, basic tools, and equipment. The Seabees approached construction as industrial process, with mechanized quarrying, automated mixing plants, and assembly line methods that produced runway sections like factory products. The technological gap between American and Japanese engineering capabilities represented different eras of warfare compressed into the same conflict. American construction operated with industrial methods, while enemy forces relied on techniques that had changed little since the previous century. This disparity created force multiplication effects that enemy planning couldn't accommodate. Positions that should have held for weeks fell in days. Supply lines calculated to be secure were cut by infrastructure that appeared overnight, and the very landscape seemed to transform at impossible speed. The acceleration of construction timelines trapped enemy forces in operational tempo they couldn't match. Defense based on natural barriers became meaningless when those barriers could be overcome in hours rather than weeks. Strategic planning that assumed predictable delays based on engineering limitations collapsed when faced with capabilities that exceeded all calculations. German and Japanese military doctrine underwent complete revision as the reality of American construction capabilities became undeniable. Traditional defensive strategies based on natural obstacles and infrastructure destruction proved obsolete against forces that built faster than enemies could destroy. A captured staff study from Imperial General Headquarters recovered during the Philippines campaign acknowledged the fundamental problem. American construction speed eliminates natural barriers as defensive assets. Strategic planning based on engineering delays requires complete revision. This recognition came too late to affect enemy strategy. Defensive positions throughout the Pacific had been cited based on assumptions about American capabilities that proved catastrophically wrong. Islands that should have been impregnable due to natural barriers fell to forces that built their way across any obstacle. The Philippines campaign provided the clearest demonstration of engineering superiority determining strategic outcomes. MacArthur's forces faced hundreds of destroyed bridges, cratered airfields, and blocked mountain passes. Japanese commanders calculated these obstacles would delay American advance for months, providing time to organize defensive lines. Instead, American engineers restored infrastructure faster than Japanese forces could retreat and prepare new positions. The Bombon River crossing, a 410-foot double-story Bailey Bridge, was completed while Japanese artillery still ranged the construction site. Combat engineers worked under fire, completing assembly in 36 hours. Major General Korochika Anami, commanding Japanese forces in Luzon, summarized the impossible situation in his final message to Imperial headquarters. Enemy rebuilds what we destroy faster than we can destroy what they build. Defensive calculations based on engineering delays are no longer valid. No revised guidance came because Japanese military doctrine couldn't accommodate the reality of American engineering superiority. Bushido emphasized spiritual strength overcoming material disadvantage, but no amount of courage could compete with bulldozers and Bailey Bridge. As the strategic bombing survey conducted in 1945 to 1946 included extensive analysis of American construction capabilities and their impact on enemy strategy. Interviews with surviving enemy commanders revealed consistent themes: surprise at American construction speed, inability to adapt defensive doctrine to new realities, and recognition that technological superiority had made traditional military planning obsolete. Admiral Somu Toyota, last commander of the combined fleet, acknowledged in post-war interrogation, "American engineers could build air bases faster than we could plan attacks against them. By the time our forces organized to assault their construction sites, aircraft were already operating from completed runways." The final irony was that enemy forces possessed detailed intelligence about American construction equipment and methods through captured documents and observation. But intelligence without industrial capability to respond proved worthless. Knowing that American engineers could build bridges overnight didn't help enemy forces counter the capability. Wehrmacht defensive doctrine in Europe suffered similar obsolescence when faced with American construction capabilities that exceeded all calculations. The Atlantic Wall, representing 3 years of careful German engineering, was bypassed by forces that created their own infrastructure faster than defenders could destroy it. The Pacific War established principles that continue to influence military engineering today: speed of construction as a force multiplier, prefabricated components for rapid deployment, and integration of civilian expertise with military operations became standard doctrine for modern forces. The Bailey Bridge system, proven in Pacific combat, became the NATO standard for tactical bridging and remains in use today. Seabee organizational principles influenced military engineering units worldwide. Most importantly, the Pacific Campaign proved that engineering superiority could overcome geographic advantages that previous military doctrine considered decisive. The deeper legacy was strategic. The Pacific Engineering Campaign demonstrated that technological and industrial superiority, properly applied, could compress the timelines of warfare itself. Enemy forces had calculated that natural barriers would provide months of defensive advantage. American engineers measured the same obstacles in days. The bridges that appeared overnight weren't just river crossings. They were manifestations of industrial power that enemy forces couldn't comprehend or counter. Each Bailey Bridge spanning an impassable river, each airfield rising from jungle in impossible timeframes, each construction miracle that violated enemy expectations represented the victory of industrial civilization over military tradition. In the end, the war in the Pacific was won as much by bulldozers and Bailey bridges as by battleships and bombers. Construction speed that enemy military doctrine never imagined possible became the margin of victory that ended history's greatest conflict. The soldiers who watched American engineers build bridges overnight were witnessing the future of warfare, where engineering capability determined strategic outcomes more than tactical skill. They had prepared to fight Americans bulldozers. Instead, they found themselves fighting American industry projected across the Pacific at construction speeds that made their defensive calculations obsolete.